Hi, you guys. It's been a while. I say that every single time I make a video because it's always been a while. I've been, as usual, super busy with work and life and a little bit of travel and my hobbies and mostly work, actually, honestly, mostly work. But I have this adorable, cute little fun physics problem that we can do. Thank you so much to everyone who's been watching my videos. I've noticed that my videos usually peak in views, usually in like September-ish, which is like the start of the academic school year, and then January-ish, which is like the start of the new semester. So welcome to everyone new, and I hope I'm teaching you something. I know a lot of you have left comments, and I'm going to try to get to them. I'm just so busy with like other things in my life. I will try to get to them eventually, most of them. And yeah, anyways, let's get started on this problem. On an essentially frictionless horizontal ice rink. I don't know if I already said this actually, but don't forget to like and subscribe. And this is from Young and Freedman's University Physics textbook. Okay. On an essentially frictionless horizontal ice rink, a skater moves at 3.0 meters per second, encounters a rough patch that reduces her speed to 1.65 meters per second due to a friction force that is 25% of her weight. Use the work energy theorem to find the length of this rough patch. All right. Okay. So you guys know the drill. You know what I like to do. I like to draw a little picture for myself just so that I can understand this problem a little bit better and sort of just highlight anything that sort of pops out in terms of like numbers and information related to the question. Okay. So let's say that is our ice rink or like our ice surface, I guess. I'm not going to draw a whole rink. Okay. So ice rink. And a skater moves at 3.0 meters per second. Okay, so let's draw a little skater at 3.0 meters per second. There we go. And this guy is going to be your skater. Encounters a rough patch that reduces her. Oh, well, it's a her, so we're going to give her a little dress. And I'm just, because I already drew the skater guy so small, um, I mean, skater girl so small, I'm going to give her a little triangle dress like I used to draw on stick people when I was like 3. And reduces her speed to 1.65 meters per second due to a friction force. Okay, so moving at 3.0 and then reduces to 1.65. So let's actually just write that down roughly. So we start at some initial speed, right? So VI, and that's going to be 3.0 meters per second, right? And then we hit some rough patch. Okay. And let's just pretend that this is some rough patch of ice. It's not the same color as the other ice. And then that reduces her speed to 1.65 meters per second, right? So she slows down basically, right? So slows down. Okay. Due to a friction force that is 25% of her weight. Okay, so slows down due to a force of friction that is 0.25% of her weight. So weight is W, but we also know that weight can be written as mg, right? So mass times gravity, that is weight. So we have that piece of information as well. Use the work energy theorem to find the length of this rough patch. All right, so work energy theorem, what's that? That is this equation right here. So total work done is equal to, total work done on a particle is equal to the difference in kinetic energy. All right. And so if you want more information and you want me to delve a little bit more deeply into this equation, you can go watch my last 2 videos. I'm not going to go into depth in this video, but yeah. All right. Okay. So now let's write down our knowns. So we have this problem where we have this ice skater, and this ice skater is starting at some speed and ends at some speed, and that's due to this force of friction. this work that's done on her, right? Because she's sort of the particle in this situation. Okay, so let's write down our knowns. And I'm just going to use a different color. Let's make it purple. And you know what? I'm just going to like annotate this right over here. I'm just going to make it known that this is the work energy theorem. All right. So we have our knowns. And our knowns are, let's go back. So we said that moving at 3.0 meters per second. So VI we said was 3.0 meters per second. And then we have her speed reduced down to VF, which is 1.65 meters per second. And that's due to a friction force that is 25% of her weight. So force of friction is equal to, as we said right over here, right? It's going to be 0.25 W or 0.25 mg, right? And yeah, that's all the information we have. So let's go ahead and let's actually solve the problem. So what we know is that we have to plug in our values, our known values. I'm trying to change the color again. Yeah, so we have to plug in all of these known values to this work energy theorem, and then we'll get the length of ice. Or sorry, we'll get the length of the rough patch. So we're looking for L, right? What is L equal to? And L is this length of this rough patch. Okay, so let's go ahead and figure that out. What is L? Well, okay, so WT, let's start off just with this equation. Let's start off with, yeah, just this equation as is. So WT, which is the total work that's done on a particle, is equal to the change in kinetic energy. So what is the change in kinetic energy? Well, let's simplify this K to what we know, which is kinetic energy is equal to half of mv squared, right? So half of the mass of an object times its speed squared, right? So it's going to be 2 or the final one minus the 1 or the initial one, right? So over here, we're going to have half of mvf squared minus half of mvi squared, right? That makes sense. Now we're going to plug in our values. So half of what's m? Well, we don't really have m here, right? So we have to keep it as is. What's vf? It's 1.65, right? And half of m, again, we don't know what this is. And vi squared, I did something really stupid, but it's not the biggest deal, whatever. I'm just gonna, okay. Well, actually, let's go ahead and just collect like terms first. That's the stupid thing that I did just because like it's just gonna look messy if I don't do that first. Okay, so we can collect like terms. So half of m vf minus vf squared minus vi squared, right? There we go. And we don't have m like we just said, but we have vf and we have vi, which are right over here. So let's plug those in. Half of m vf, which is 1.65 squared minus 3.0 squared. And that is the change in kinetic energy, right? But we're looking for the length of this rough patch. And I don't know about you, but I don't see length on either side of this equation. So how do we get length? All right, so now we have to dissect this equation a little bit further. Now, what is WT? Yes, it's the difference in kinetic energy, but what is the total work that's done on the particle? And in this question, we're given that information. The total work done on the particle is due to the force of friction. So let's, right here, due to a force of friction, that's the work that's done on her. Okay, so total work done is the force, the dot product of the force of friction with the length of the rough patch, right? And where did I get this equation from? Well, this is like a textbook equation. You have to memorize this. Work done. I don't know which chapter it's in. I feel like it's chapter 5 or probably 6. I don't know. Look that up. But the work equation is essentially, well, it is the dot product of the force and the length that that force is done on. That's like the work that's done. Okay, so you can also find it in my older videos. All right, so we have force of friction, right? And that is 0.25 times mg, right? Dot product with the length of this rough patch. Now, one more step, right? So let's take the dot product of these two terms. Now, the dot product of these two terms is going to be, let's draw out the vectors. So if we have this is the length of this rough patch, right, and the skaters moving, this direction, then the force of friction is actually going to be working in the opposite direction, right? Because friction is slowing us down, and we know that friction works like against an object. And that means that if we look at the dot product between these two vectors, right? If we look at the angle between these two vectors, that's going to be, if this is theta, that's going to be theta is equal to 180. And this can be, dot product can be rewritten as, magnitude. So magnitude, and then the multiplied by the angle between the two vectors, which is cos 180. And that means that this is going to be minus 0.25 mgd, right? And I go into a little bit more detail on this little thing in my last video, so you can definitely check that out if this was a little bit too fast. But anyways, moving on. So now we know that the work, that the total work done on this particle being the skater, is minus 0.25 mgd, right? Where d is this length of this rough patch. So I realized I just did another dumb thing, and I went from calling this path length, this rough patch, L, to calling it d. It really doesn't matter. Like, just call it whatever you want, A, B, C, D. Essentially just for our purposes, right? Okay, anyways, so WT, we have what the total work is right over here, and we also have it right over here. And because we're trying to find, this length of this rough patch, we can just set these two equations equal to each other and isolate for this term right over here, and then we'll have the length of the rough patch. All right, so let's look at it. So, or let's solve it. Sorry, it's getting late. Okay. Okay, let's use this color. So now minus 0.25 mgd is equal to half of m, 1.65 squared minus 3.0 squared, right? All right, so we want to solve for d. So let's isolate for d and also simplify this equation. Right off the bat, we notice that we can just cancel out these two m's, right? And let's isolate for d. So d is equal to half of 1.65 squared minus 3.0 squared. And then we divide both sides by minus 0.25 g, right? And we know that g, because that's gravity, that's equal to 9.8. And so we just plug in our values, right? And we get, and I'm going to write it in pink, my favorite color, D, or L, I guess, right? And then now that looks like D divided by L, no. D, or L equal to D, whatever you want to call it, is equal to, let's plug that into my calculator, which sucks. Let my family borrow it, and now it barely works. All the like the printed numbers have been rubbed off, so I barely know what I'm punching in. Okay, so I just got that this is equal to 1.28 meters, right? Which means that the length of this rough patch is 1.28 meters. And that's the solution. I hope that was helpful. If you have any questions, of course, feel free to send me an email or comment it, and eventually I hope I'll get back to you. But I really do appreciate your comments, and I appreciate your likes and your shares. Thank you so much for watching. I hope this was helpful. Please don't forget to like and subscribe, and see you next time. Bye.